enter the room. So let me just briefly introduce the session. This is session 3, Autonomous Vehicles and Transportation Infrastructure. My name is Jason Hawkins. I'm an assistant professor at the University of Nebraska-Lincoln. As of September, I'll be moving as an assistant professor at the University of Calgary, and I'll be chairing this session. We have a few presenters today with some unreliable internet. So we'll have a few that will be presentations, will be recordings. But I know at least our first speaker is here to answer questions after the presentation. So let me just very briefly introduce our first speaker is Dr. Jinping Guan, who's a professor at Harbin Institute of Technology. She was a researcher at MIT and now a research affiliate at MIT and Harvard University. She's the Deputy Director of Research and Development, the key technology and equipment industry of Intelligent Vehicle Road Collaboration, the Minister of Transport in China, and also a member of the organizing committee for BTR. So thank you, Jinping, for your contributions to that. And her research interests include travel behavior and policy, transportation system analysis, big data, cloud computing, the impacts of mobility as a service and autonomous vehicles. She received her PhD in transportation planning and management from Tongji University and the University of California, Berkeley in 2015, and has a bachelor's in economic geography and urban planning from Sun Yat-sen University. So Donia, if you want to maybe share your screen, and you should also need to share the sound with that presentation. When you shared your screen, Donia, did you also share the sound?
Sorry.
Did you share the sound as well? There's a little, you have to click a little box for that.
Yes, I'm mute. So you can't hear that?
No, here, I can share it. It might be easier that way. Here, let me do that. It's just.
Okay, so good morning, everyone. I'm so happy to be able to present our recent research on the willingness to pay for the automated vehicle subscription and insights from the current population in China. Okay, can you see my screen? I think everything is working. Good. Okay. So this research, the paper has been accepted by the Transportation Research Part A Policy and Practice. So if you're interested in the further details, feel free to search like the name of the paper, and you'll be able to see online very soon. Couple of things. So first, this paper we focus on the study. We focus on the willingness to pay, and it's for the automated vehicle subscription. So you're gonna ask me, what is automated vehicle subscription? Is it like a phone subscription service, or is it like a TV show subscription? So we'll first give a definition about that, and this insight is drawn from the Chinese car-oriented population. So I would define what is a car-oriented population, and we focus on the respondents in China. So simple outline, we're going to talk about definition, key findings, and I will go to the details of this willingness to pay study, and then some takeaways. All right, so first, in this study, we focus on the level 4 automated vehicle. It's the same definition from the SAE automated vehicle level 4. So this is the respondents when they participate in the survey online, this is the definition they will see. So for example, we give here self-driving cars are safer than regular cars. We just give this assumption to them, so then they know roughly in the survey, what do we mean by the self-driving cars? It's all this definition here, it's the exact same as the level 4 automated vehicle according to the SAE. Okay, and then we asked them, it's important for us to make sure that we have been clear about the definition of the self-driving car in the survey. So we we let them answer these 4 statements and which ones of them are true. So then to make sure our respondents, the people in our survey, they fully understand what do we mean by level 4 automated vehicles. So if they couldn't answer these questions correctly within 2 attempts, the system will remove them, so then they won't be in our sample. So that's how we make sure we get people to fully understand what is level 4 automated vehicle. And then the study focused on cognitive population. So it's the people who drive in a personal vehicle for the most frequent trip. And also this willingness to pay, it's for automated vehicle subscription. So this service, it's like you pay the subscription fee monthly or yearly, and then it's similar to leasing a car for a longer term at a cheaper price. And you use various car models. After, say, for example, 12 months, then you can change your car models. And it is basically your own car, and you use it as long as you pay for it. So video, let's see.
Imagine there was another way to enjoy a luxury car experience. What if you had no down payment, no price negotiations? Just one flat monthly rate that includes everything you need, like insurance and maintenance. What if you had access to a concierge service 24/7, designed to make your life easier? What if you could change your car after just 12 months? It's as easy as getting a new phone. Cars are all about freedom.
So this automated vehicle subscription, the definition and like the wording we just seen before, and also this video was shown to the respondent to make sure they understand this level 4 automated vehicle and the automated vehicle subscription service. Yep. So then I will move on to talk about more about the highlights, the key findings in our study, to just flash you with the main takeaway points. So according to our survey, the percentage of the current population, like these respondents, that they are willing to pay for the positive amount of value, like they're willing to pay for the automated level 4 automated vehicle. As you can see here, if the automated vehicle is privately owned, 96% of them, the current population, the respondents are willing to pay for a positive amount for it. And if it's an automated vehicle subscription service, all 100%, all people are all respondents are willing to pay for this. And if it's shared automated vehicle, so it's 71% lowest amount, these 3 modes, they're willing to pay for the service. And the median willingness to pay for this automated vehicle service, these 3 different ownership modes, you can see an extra 130K China yuan, and compared to like a regular vehicle. So this is the how much the respondents are willing to pay extra for the automated technology if the vehicle is self-owned, like privately owned. And if it's this automated vehicle subscription service subscribed, we are willing to pay 3,000 China yuan per month. And if it's the shared automated vehicle, which means you don't own it, just kind of like a taxi or Uber, Didi comes to you and pick you up, and that's about 400-ish China yuan per month. So the business purpose and high income group show a strong inclination towards the automated vehicle subscription. And this, we take the short term of AVS to represent automated vehicle subscription service, and it is shown to be a promising path forward in AV adoption. So these are the highlights of the study. Let's go to some of the details. So for this study, we'll talk about the project outline, the data, the project overview, the data overview, and some results and future work. If you're interested in the exact mixed logic model that we use, or exact state preference survey methodology, the conjoint part of the survey. So if you're interested in details of that, feel free to search this title that's down here, and it will be online very soon. It's accepted by the Transportation Research Policy and Practice Journal to be able to see a lot of the details online very soon. So the objective is to understand the impact of level 4 automated vehicles on the car-related travel mode choice for the car-only population in China using state preference data. And the research approach is that we did the statistical analysis of the Chinese AV data set. We estimated the discrete choice model, and we did the model evaluation and draws conclusions. And the general idea is basically the automated vehicles' impact on travel mode choice should be included in the urban transportation planning, for example, in the demand modeling system, and also to estimate the discrete choice models to understand these impacts will be really helpful for our city planning and transportation planning. So the data we collected, as you can see, that's where the samples are, the respondents are located. It's an online survey. We use stratified sampling method, and we collected 760. That's the sample size. And this is a choice-based conjoint. So we say, imagine your current vehicle is no longer available to you, and you could choose from the following travel modes. So these are our dependent variables. So it's either to buy a regular car now, or to buy an automated vehicle, or to buy an automated vehicle subscription, or a shared automated vehicle. So which one would you choose? So each participant answered 4 experiments. So the attributes we provide to them in the survey, they're able to see the in-vehicle travel time, the origin and destination, 2 parts of out-of-vehicle travel time of each of the modes, and then their trip costs, parking costs, and the fixed ownership cost of the regular car and the self-owned automated vehicle. So this is like the cost once you have this car with you, you will pay it no matter you use it or not. And then the monthly subscription cost, that's referring to the automated vehicle subscription and the share automated vehicle. So these are the attributes that the respondents are was reviewing or looking at the survey. So after data cleaning, we have a data set of 471 participants. So each of them, remember we said they answered 4 experiments. So that's this amount of experiments that we have right now in the data set. So some results, we find out that more than half of the respondents have little or no knowledge of automated vehicle. But however, they accept the automation level of level 4 or higher. And then the majority of them have a somewhat or to very likely to try a purchase an automated vehicle. This is the Chinese car population. And we also asked them a multiple choice about like, assume that all the following transportation mode will become automated. So we're assuming travel time and cost, etc. stays the same before and after, and which are the ones that you will use for your one most frequent trip. And they answered the most frequently selected automated modes are self-owned automated car and the automated car subscription. And the least interest goes to the automated public transit. Okay, so after the statistical analysis, we estimate a discrete choice model. So this is the mixed logic model. The dependent variable is the 4 modes that we talk about, assuming your current vehicle is no longer available to you, which is the one that you're gonna choose. And we use a mixed logic model, the random error term, like we assume normal, to be able to capture the regular car, the self-owned automated vehicle, and the automated vehicle subscription, like this correlation among these 3 modes. And this is the structure of the mixed logic model. So some model results. I will go through the findings from the model results Just a moment. Okay, so first, from the model results, which I just showed here, we calculate the value of time. As we can see here, the value of time doesn't vary much, and then amount of modes. And since it's it falls within the range of the existing Chinese automated vehicle state preference study. So the value of time is comparable to the literature. So then we move on to see, for willingness to pay, how much are people willing to pay for that level 4 automation? So we target this question from 4 different angles. One is, what about different AV modes? Like we talk about like self-owned, subscribed, or shared, or you can just continue to buy your regular car. What about by trip purpose, or by annual household income, or are there any like adequate effects? So from these 4 angles, we try to answer this willingness to pay question. So let's first take a look at the modes. So this is the key finding, the takeaway, like the highlight page I showed to you at the beginning of the study. This is where the result, how do we get this result? So as you can see here, the AV subscription service, all the respondents are willing to pay for the service. Comparatively, the lowest goes to the shared automated vehicle. And the median is calculated, the median willingness to pay. And then by trip purpose. So as you can see here, the business and commute trips may be the target market for automated vehicles subscription. So this is the self-owned AV, this is the automated vehicle subscription service, this is the shared automated vehicle, and this is the median value basically calculated. So that's the conclusion we can draw from these figures. And then if we move on to how about annual household income, we can see here still same automated share self-owned automated vehicle subscription, and this is the share automated vehicle, and this is the different income level, and then the median levels, the median value is shown in this table here. As you can see, as the willingness to pay increases with income for the self-owned AV and automated vehicle subscription service, and for the shared automated vehicle, people who have higher income actually have a lower willingness to pay for the median value for the shared automated vehicle, which makes sense, right? And then the attitude effect. So we have these 4 questions in the survey, and then if the person answered the first one to like strongly agree, and then the 2, 3, 4. So if this or these 2, 3, 4, these 3 questions, they answer it all at somewhat agree or strongly agree, then we will consider them a high level of pro automated vehicle. So they have this attitude. The rest of the respondents goes to the other low level of pro AV attitude group. So as you can see here, this is the self-owned AV, automated vehicle subscription service, and shared automated vehicle. So we calculated the mean, the median, and the percentage of this in this group. The percentage of the respondents that has the positive, that have the positive willingness to pay. So as you can see here, the pro AV attitude is impactful on the willingness to pay, especially for the self-owned AV. As you can see, a little bit. And then this part, if it's the shared automated vehicle, it doesn't have a lot of difference. So that's the attitude effect. So if you want to see more details about this, please go to you can see more details of this if you search online from our paper title as listed here. And the key findings are basically private AV modes are preferred, and the AV subscription service, the automated vehicle subscription, is the most attractive. And the business and commute trips may be the target for the automated vehicle subscription. Our willingness to pay increases with income for the self-owned AV and the AVS, the automated vehicle subscription. That's what we just seen from the figures. And pro automated vehicle attitude has a positive effect on willingness to pay, especially for self-owned automated vehicle. So four different aspects, right? We consider them different modes, different purpose, and different income, household income, and also the attitude. So these are the four key findings of our study. And then the main takeaway that I want to bring you back to the picture that you've seen at the beginning of this talk. So three different modes. The subscribed one has 100% the car-oriented population respondent in China. They're willing to pay for it. And the median willingness to pay for an AV are shown like here. So we are able to calculate the value using the mixed logic model and some formulation to do that. And the business purpose and high income, like these groups show like a stronger inclination towards the automated vehicle subscription. And automated vehicle subscription from our study is shown to be a promising path forward in the automated vehicle adoption. And some of the future work. So for example, to explore the hybrid choice model to better capture the effect of latent variables. Right now, we didn't have this integrated choice and latent variable model estimated. We're working on it. And then the random parameter can be used to capture the unobserved heterogeneity. And so we are doing a next study, which is trying to do the automated vehicle travel demand modeling. So for example, here, the needs we consider as latent variable is like as a motivator of the human activities. So we want to move from activity-based travel demand modeling to using the needs-based approach. And second is that in the middle, this is 1 to 7 days. This is the needs psychological inventory. So we want to move from average 1 day travel demand modeling method to have multiple days and being able to capture this non-myopic decision-making process of the individual travelers. And then also we want to move from sequential to simultaneous decisions, such as travel, let's say activity participation, location, duration. So these are some of the work we're doing and we're consider doing next. And with that, thank you very much. You're very welcome to reach out to me if you're interested in this research effort, and welcome to join us. And I was awarded this excellent use overseas grant from the Chinese National Nature Science Foundation. So we have funding secured. And then if you're interested in research, definitely reach out to me so we can have more in-depth research collaboration. And my contact information is this email and my WeChat on the screen. And if you're interested in the paper, you can search the title of this presentation and you'll be able to see the paper online very soon. It's accepted, so we're working on getting it finally published online very soon. Okay, so with that, thank you very much, and let me know if you have any questions, thoughts, and comments.
Great, thank you. So we're a little bit tight on time with 6 presentations. I think Jinping's answered some questions in the chat. Are there any questions that we want to maybe answer? Okay, so there's I just see one question here that we can maybe answer live. Okay, Jinping said, so if you have questions, feel free to post them in the chat. And we will move on to our next speaker, who I believe is going to be Javier Pena-Bastidas, speaking on behalf of a team at the University of Alabama. Sorry. This paper is led by Ziha Zhang, but Javier, who's our speaker today, holds a bachelor's degree in industrial engineering and a master's degree in civil engineering from the National University of Columbia and the University of Los Andes, which are 2 of the most prominent universities in his home country. He's currently pursuing a PhD in civil engineering at the University of Alabama, Canadian brain, Alabama. His research interests lie at the junction of transportation and urban planning, and exploring how these areas relate to the well-being of societies. Now, I think, all right, will you be presenting live? I believe we also have a record.
So I have she has presentation.
Okay, great.
So you want me to play the record for her, or because we have two presentations in this session, I will be the last one and she
Okay.
is in this moment. So I
Yeah,
have her presentation. If you want, I can do
share
both.
her presentation. Let me do that.
Okay.
Yes, I think that's the one. Just correct me if I have the wrong presentation here. But... Okay. Here we go. And I want to share. Where did that go now? Right. No. I have it open. Why is it not showing up? Let me just share the screen again.
Hi everyone, I'm Zihe Zhang from the University of Alabama. Today I'm very excited to share with you our latest research, which is about shared autonomous electric vehicle simulate in small and mid-sized urbanized area in America. I would like to thank to my co-author, Dr. Jun Liu, which is the corresponding author of this research, and also Javier and Dr. Stephen Jones. This research has already been published in Transportation Policy. You can feel free to access the paper by the QR code here. Let's get started of this presentation to show this research. Though I think majority people during this session might be very familiar with the conception of the shared autonomous electric vehicle. Let me give a brief introduction of the SAEV. You can regard SAEV as the autonomous electric vehicle which provide mobility service to travelers without the car ownership with the travelers. So you can regard it as like driverless electric vehicle. Actually, in many cities like the Phoenix, Arizona, and also many cities in China such as Shanghai and Wuhan, such robotic taxis have been already implemented in the city to provide mobility service to travelers, though the speed may be a little bit lower than the human-driven vehicle, but they provide much cheaper and convenient service to travelers. And we anticipate that such kind of mobility service will enter more cities all over the world to provide convenient, sustainable, and much more inexpensive urgent mobility service to travelers. In the transportation planning field, there has already been studies to in this SAEV areas. In very early research, the simulation are based on the simplified, or we can call it hypothetic environment, such as the uniform distributed population and also the grid-based road network whether it is like circle based or the grid based. So also maybe it also simulated in a limited context. For example, a corridor, geofences area of the service. And most recent simulation started to based on the real world travel demand and also the real world network, but still they only anticipate such service to be provided in very large cities or great metropolitan areas such as the New York City, also Atlanta, great metropolitan areas, also other countries like US, such type of cities with very high travel demand and dense population. But think about that. If the technology become mature, there are around 400 urbanized and urbanized areas in United States. You can see that figure shows the location of these areas. This area can also be benefit from the shared electric autonomous vehicle. People in these areas, the U.S. people living in U.S. can also benefit from the mobility service. For this area, this area are not feasible or not feasible for the developing of the SAEVs. Maybe there is not a one size fits all criteria because the shape of the network and also the travel demand, the network density also changed. So you can see the visualization of the network, road network. Their shape totally changed. So we are curious about for those small and medium-sized area, the total number around 400 with a population between 50,000 to 375,000 according to the American Community Service data 2019 data. So for this area, will such area also be benefit from the SAEV service? We're curious about that. And we think that because for this area, the network varies a lot, their land use very large, also the population density. So we think about that, their performance will vary among these different cities. Here shows the conceptual framework of our study. The basic idea is very similar to the commonly simulation study, that is input the demand data, road network data, output the fleet operation and the charging operation data. But after that, we're curious about which factor will influence the performance of the SAEV. So we're going to build statistical models to show the relationship between the factors, basically their travel demand features and road network features, how they will influence the SAEV system. And our expected outcome of this research show the range of the SAEV fleet size and also the required charging station for the simulated small and urbanized areas. And after that, we are going to build models. We will have knowledge about which factor will influence the performance of the SAEV, which factor will influence the performance of the charging station. After that, we know the factors will have positive impact and negative impact so that we can raise the localized countermeasures or suggestions for the interested sector if they want to implement or provide SAEV service for the small and mid-sized urbanized area in the United States. The research objective specifically is to determine the range of the variation of the SAEV's fleets as well as the charging infrastructure and also finding the factors provide the knowledge as we mentioned. Here shows the simulation, the basic simulation methodology, which is we input the road network and also we synthetic the trip demand data. Specifically, I want to mention that the demand data actually used in this study is a commuting demand. Commuting demand is now cannot representing all the travel demand, but because commuting demand is more stable and more predictable, it is actually commonly used to simulate the travel demand, especially for the emerging mobility service. For the road network, we have two sets of data. For the first set of data is real network. It's representing a network by the node and linked to reflect the actual road network on reality. And also, we also use reference Dr. Boyne's data. In his research, he provided the open access data set representing the network by the graphic measures. You can see here, it including the edge count, node count, edge density, node density, as well as other graphic measure. For the road network data, for some of the data, they may highly correlated with each other. As we mentioned, we are going to build statistical models, and collinearity may generate the bias result. For example, the edge density may be highly correlated with the street density, intersection density, and node density. So we use reduced dimension technology, which is commonly used in both statistic modeling and machine learning, called the principal or component analysis. After that, the reduction of the dimension, generalized 5-dimension, network size, network density, network connectivity, network complexity or regularity, and network vulnerability. For the synthetic commuting data, we generated separately for each urbanized area based on the OD data and also the survey data. The survey data shows the trip distribution and also the start time distribution. Here, let's take a look about the agent-based modeling of the SAEV fleet operation. You can see 3 colors very clearly. First, you can see the black color. It shows the procedure, simulation procedure for the simulation of the SAEV fleet. The orange color, the golden color, actually, it shows the checking of the current battery range to determine whether it should be recharged. And also the blue part shows the charging infrastructure simulation. The parameter of the simulation actually is very important in all the simulation study. Here shows some assumed parameters. You can say SOC representing the battery range and the status of battery range. It means, for example, the minimum SOC status of battery range is 20% and maximum 80% according to reference. And we assume that the full battery range is 150 miles. For the fleet operation and charging performance matrix, we adopted the commonly used matrix from previous study. You can see that it including the required fleet size, number of trips per vehicle, empty vehicle, VMT per vehicle, occupied VMT per vehicle. For the charging performance, we're curious about how many charging stations in total we need, and also the ratio of vehicle to charging station. how many trips request per station, how many charging spots per station. So after talking about all the simulation setting and the simulation framework, based on that, we simulate the performance of the 384 urbanized small and mid-sized urbanized area. We simulate the level 2 charging and level 3 charging. The difference is that the charging speed is different. Actually, level 2 is much faster than level 3 is much faster than level 2. Here you can see the range of the fleet size and different metrics vary allowed around the multiple small and urbanized area. That shows level 2 and level 3. Here we also mapping the metrics based on the location of the small and urbanized area. We pay attention to the key metrics. We want to see their variation. So you can say this shows the average number of trips or service per vehicle separately for level 2 and level 3. And you can see that the top 5 regions for this matrix, and we can also figure out that actually level 3 show better performance. These slides show the percentage of MTVMT. This slides show the trip request per charging station, and clearly, as expected, we can say that the level 3 charging station can serve way more trips than way more trips than the level 2 charging station, which is reasonable. And we can see that ratio of vehicle to charging station, it is similar to ratio of trips as we just showed. Here we show the simulation based generated the charging station locations. You can see that for level 3 it generates less charging station because the charging speed is quicker. And also we figure out that the spatial distribution of the charging station actually is closely related to the shape of the road network, the shape of the urbanized area, which is very reasonable and it's as expected. As we mentioned, we are going to build models to quantify which trip characteristic, demand characteristic, and road network demand characteristics to influence the performance. We built 2 sets of models for the 3 key metrics we're curious about, which is the trip per vehicle, MTVMT, and also the ratio of charging station. And for each of the metrics, we input 2 sets of factors as mentioned. The first one is the row graph metrics, and in the final model, we only show the statistic significant factors. And also we input the reduced dimension factor. As we mentioned, the 5 reduced factor related to the road network, like the connectivity, the vulnerability, produced by the principal components analysis. Here shows the correlation of model 1 and model 2, and based on the model, we can clearly say which characteristics are better related to the better performance of SAEV, similar as the rest. So we have some limitation of this research about the travel demand, the road network, the charging station, and also the parameter assumption. For the takeaway, as we mentioned, we see the variation about the fleet performance and also the charging performance. So localized countermeasures and suggestions need to be taken to better fit the city. And also level 3 charging station better performs level 2 in many key factors, which we has already shown. Here shows some implementation about the spatial variation and also the fleet performance and localized suggestions of the implementation for the interested sectors. Besides for this research, we based on the synthetic trip demand data, we have such data, and people or researchers who are interested can contact Dr. Liu's lab, Next Generation Transportation Lab. Thank you for listening. If you have any questions, please feel free to ask my colleagues Javier's, and hope you get the satisfied answers. Thank you so much.
Great, thank you. So again, maybe just in the interest of time, we'll transition to the next presentation and we can answer questions in the chat box. So I guess, Felix, would you like me to play the video or?
Hi, Jason. Thank you for sharing. Yes, please. I already disconnected twice from this session, so I would be glad if you could launch the video instead of me presenting.
Sure. No, sounds good. So just very briefly, Felix Carrier is a ex-strategic department of the French Railway Company, PhD in economics, has worked around simulation, economic evaluation of transport projects, and is currently a project lead managing projects and research teams. So let me open this and share my screen.
Hi, everyone. From France, and I'm here to speak about the autonomous vehicles in a periurban area with the help of an economic appraisal, which is named the cost-benefit analysis.
There we go.
Before to start, I would like to thank our host for leading the session, and I will now introduce the definition of autonomous vehicles. They're the kind of vehicles that can drive themselves. That means that we give them the ability to take decisions in our own place. It has a lot of implications. First, that people do not have to drive themselves. Second, that we can maybe, in certain kind of transportation services, avoid to use a driver and then save the cost of a wage to provide the service. So what are the implications of such vehicles? We'll just review them very quickly. I know that a lot of you are aware about those topics, but let's go to a quick review. The benefits and costs expected to result from the introduction of autonomous vehicles are numerous and will have a repercussion on the whole mobility ecosystem. First, on the traffic. They may be able to drive better than us, but we don't know that for sure right now. But it would allow to help the flow of the traffic, thus limiting the congestion. For the users, if you have to take a drive somewhere, it might be more comfortable to have a car which drives itself than you driving yourself. So it may change a little bit your habits of mobility. As for the operators, the gains are quite clear. If you do not have a driver, you save a wage and then it's cheaper. It means everything equal, it will be more profits. From the infrastructure, that is something that is remain to be think. We do not know right now what is the level of infrastructure connection that we need to have. So for now, it's still a question which needs to be answered, and that's something we want to do a little bit in this work. Lastly, the environment. If we change our habits of mobility, it might result also in a change in greenhouse gases emission, local pollution, or even road safety. So that is also something that we want to see here. So for this study, we will start with a rather simple state of the art, go through the methods, results, and conclusion. As for the state of the art, it has been through a literature review with a question which was how were the automated vehicles were evaluated. To do so, we looked into the socioeconomic evaluation of AV in simulation literature. It led to a bibliometric analysis of 84 articles. But then we wanted to explore the question, how could we evaluate such a service which for now does not exist? And to do so, we pursued a meta-analysis of the main indicators that we can find in simulation studies. So there were the vehicle kilometer travel, the travel time for the user, and we gather all this information. And what we found is the fact that, firstly, the autonomous vehicles were mostly evaluated through operational or service performances indicators. But when we look into the studies of externalities generated by such services, or the evaluation of a more thoroughly thought investigation of the economic performances of those services, we had much less papers treating the topic. So we also looked into the performances of such services compared to their conventional counterparts, such as a classic car, private car. And what we found is that if we replace, the cars by AV, whether they would be a solo ride AV, which are the AVs on the slide, the green one, or shared AVs, which are the gray one on the right, both would increase the travel time on the travel time. It is the rebound effect that I was talking about earlier. If it's more comfortable to use an AV than a car, people may want to use them more. In the other hand, having those vehicles may allow to diminish the fleet size required to serve the exact same demand. The diminution is much higher when the rides are shared. I think I don't have anything to add about that, and everything might understand it without any help. So, in this study, what we've done is we started from another study, which is the development of a cost-benefit analysis methodology, working hand in hand with a nation-based simulation model, and that we applied on the city of Berlin. Here, on the presentation today, we will speak about the intermodality between SAV, which is shared autonomous vehicles, and public transit, because it is almost never been done for good reason. It is quite difficult to do in a simulation. You need a lot of data, you need a lot of computational power, and you also need the good algorithm. So here in C2D, we will apply the cost-benefit analysis, which is already been developed. And we will apply it on a shared autonomous vehicle service, acting as a feeder service to a train line. So the cost-benefit analysis structure is a structure such as, first, we have the economic agent, which are the consumer. And we will look into the variation of their surplus through the log sum time equivalent methodology. As for the operator, we will consider 3 items. First, the infrastructure. Second, the vehicle fleet investment necessary to launch the project. And then the operational cost of operating those services. Then we look into the externalities and the life cycle effect, CO2 emissions, the road safety, and the noise nuisance. So quite quickly. Let's see the items retained. As for the infrastructure, a cost of 250,000 euro per kilometer were considered. It is only the equipment necessary to drive for autonomous vehicles and not the cost for conventional cars. So it is additional cost. As for the vehicles, we consider two kinds of vehicles. First, a car, which would be a little bit less than 40,000 euros, and then a shuttle, which means a vehicle with 8 places, which is developed in Europe, in Germany and France mostly. As for the operational cost, it's of almost 50 cents for the car and a little bit less than a euro for the shuttle. If we look into what is the performances of such services, compared to conventional cars, the consumption, the energy consumption would be a little bit lower due to smoother driving. For the local pollution, what we found is the fact that they may also want to reduce that amount, again, thanks to the smoother driving. As for the life cycle effect, if we look into this, we can see that autonomous vehicles require a little bit more of technology, computer, and energy to feed those technologies. So the life cycle effect is a little bit more important for AV than for conventional cars. And here we do not consider the impact of infrastructure. As for noise nuisance, it may be a little bit unconsidered for now, and we don't have any much data on the topic, so it would be traffic based. And as for the safety, we consider that 20% reduction is an accident. Would like to say that the safety may be a little bit overrated for the AV right now. We don't have any much data, and a conservative approach has been taken. So we paired a mobility simulation with the cost-benefit analysis. So we will use the mobility output to feed the cost-benefit analysis. And the simulation that we will use is an agent-based simulation. So people are trying to reach their goal with the help of a score. And they will try at every iteration to find a better alternative until we find an equilibrium, and we then use the output to feed the cost-benefit analysis. So the use case was a Periurban area near Paris in France. It is a place served by a very heavy line train, which we help through the implementation of AV service. So we have 4 scenarios. All of them are based on ride sharing. We have 2 kinds of vehicles, either car or shuttle. And we also explore the operational schemes, either in door-to-door or in stop-based, where you have, based on the public transit network of stops, a destination where you can go almost 200 to 400 meters from your home. So it would allow to maybe use a little bit less of the cars and to make less detour to get passenger. So the result of the studies, we were looking into the travel time. Such implementation of service would allow to decrease the transit time of the public transit user, because it takes modal share from public transit mostly. But the biggest thing is the raise in the travel time from private car users. It is because that you may find congestion when you add new transportation on the road, and TRV are not the good solution to avoid this kind of result. So what we found for the AV services is the fact that when you go through our core services. The two first ones here are core services. The fact that you have a lot of difficulty to get your cars at more than 2 persons per car in average. Even though the filling rate, the average occupancy rate is quite important, it is in fact much more important than what we can find in the literature. The shuttle, when paired with the transit line use, are much more efficient. So, if we look into the CBA analysis, for the consumer, the SAV implementation is still good despite the increase in travel time, because the SAV are much more comfortable than the public transit. As for the financial expenses, implementing a new service will always cost something, but what we can see and learn today is the fact that infrastructure investment will maybe be the biggest cost. As for the externalities, what we can see is also that the model shift toward AV coming from public transit also does not help to reduce externalities, and it is in this case a loss in all sub-item of the CVA. So if we look into the net present value, what we can see is a quite nuanced result, where the consumer surplus may be a little bit overestimated in this case, depending on the utility function of the users. And we have to develop a little bit more the topic and to go through maybe the last thing, the conclusion. So feeders SAV services may attract a lot of people in peri-urban area when working in coordination with the train line. The equipment and infrastructure can represent a very important cost which need to be considered. Lastly, the stop-based operational scheme allows a better vehicle occupancy, and we need to be looking, and we will need to look into that later. Finally, for the empirical contribution, we've done the implementation of a feeder SAV service, which is quite uncommon. We paired an economic evaluation of such a service in a peri-urban area with a nation-based simulation tool. And we also considered the operational scheme of a stop-based infrastructure, which is, from my perspective, very promising. Lastly, we want to look into more SAV service scenarios. We will consider a configuration of a consumer surplus per user group, and also look into pricing policies to mitigate the externalities and the increase in traffic flows. Thank you for your attention, and I'm waiting for your question. Thank you.
Great, thank you, Felix. Are there any, we maybe have time for, let me get back to that. Oh, I see. We maybe have time for one question sort of live if Felix would like to answer a question live, or we can do them continue doing them by chat. Are there any questions that anyone has? Maybe just Martin Schmidt is asking, Felix, what did you include in your infrastructure costs?
Hi, can you hear me well?
Yeah,
Maybe shut down the camera if you do not hear me well.
Yeah, I can hear you.
Okay, so about the infrastructure cost, I want to admit that my research went bad, and I didn't find any valuable data. So if you look into the article that we already published on the Berlin study, I discussed the topic a little bit, and I choose to address the fact that we don't have any data by just giving an arbitrary amount to start thinking about it, because this is a topic that nobody wants to talk about for one good reason. It might cost a lot. So I just want people to start talking about it with arbitrary data. It would be, I want it to be a stepstone on the discussion. But I'm currently leading a new project where we are going to assess the cost for the infrastructure depending on the type of services. So there is a camera, leader, and for now we found that the infrastructure cost equipment was heavily related to the crossroads and not the millage. So it's not about having a long road, is having about a road which have a lot of intersection.
Great. So I think there's a few other questions in the chat box. Maybe just in the interest of time, I'll let Felix answer those.
Yeah, for sure.
In the chat.
Thank you for having me.
Our next two speakers, I believe our next three speakers will be live. We're a little bit behind time, but I think we can catch up on time. And so our next speaker is going to be Kentaro Mori, who is you a PhD student, is that right, Kentaro?
Yeah, that's correct.
Yeah, okay. He's a PhD student at University of Texas at Austin with Professor Kara Kaufman. So Kentaro, if you want to share your screen.
Sure. All right, can you see the screen?
Yep, go ahead.
Okay, yeah, thank you, Jason, for the introduction. So, yeah, my name is Kentaro Mori, and this work is in collaboration with my advisor, Dr. Kara Kalkoman, Dr. Fatima Fakhamisavi at UConn, and Oregon National Lab researchers, Dr. Krishnamurthy Gurmurthy and Dr. Pedro Camargo. And we explore a question that is quite fundamental. How do network completeness and OD addresses details impact traffic and shared autonomous vehicle fleet operations? And just to set the scene, I have an extreme example here of the classic Sioux Falls network versus the actual Sioux Falls Road network. So we make all sorts of simplifications as travel demand modelers. Either it's in demand side by downscaling the population, or on the supply side on the network by using network with some local links omitted, or by aggregating potential origin and destination points. And we do this to keep the computational times reasonable. But oftentimes we don't really understand the consequences of these reduced realisms, and this can hurt our understanding of network use, congestion and queuing, mode and destination choices, SAV and transit system operations, and so on. And in this study, we address the implications of supply side simplifications. So here we have two versions of the 6-county Austin, Texas network. On the left, we have the one that is used by the Capital Area Metropolitan Planning Organization, abbreviated as CAMPO. It has around 16,000 links and 13,000 nodes. And on the right, we have this network for the same region that is obtained from OpenStreetMaps, and it has almost 10 times the amount of links and nodes. And in terms of lane miles, the Campo network contains 67% of the lane miles contained in the OSF network. Here we'll look at the same thing for addresses or locations. On the left, we have the Campo locations. There's around 40,000 locations for a population of 2 million. And we can obtain all of the addresses in the region actually from open addresses, and which is around 23 times, almost 1 million addresses. So in this study, we're using Polaris, which is an agent-based simulation framework developed by Oregon National Laboratory to simulate 2 million travelers and shared autonomous vehicle fleet operations in the Austin 6-county region. What Polaris essentially does is it simulates the 24-hour day of activities for a size population and routes them through the network using dynamic traffic assignment. Also, there is a fleet manager that gives assignment, operation, repositioning instructions to shared autonomous vehicles, considering the evolving network congestion states. Briefly go over how I set up the simulations. I used a fixed demand table developed in the previous study by Matt Dean, and using a fleet size of 15,000 shared autonomous vehicles, which is around one SAV per 125 residents. The OSM network was converted to the native Polaris format using a combination of OSM to GMNS developed by Lou and Zhao, and Polaris Studio, which is a Python package used to run and set up Polaris simulations. The open addresses locations were matched to the closest Campo address for distributing trip origins and destinations from the fixed trip table. And in the bottom figure demonstrates how these were matched. So there are some differences in lane counts, speed, free flow speeds, capacities, and intersection interchange geometries and controls between the Campo and OSM links. And in order to eliminate these differences, we extracted the same links that exist in Campo from the OSM network. On the bottom table shows the 3 networks that were compared in the study. In terms of the total lane miles by facility type, and intersection controls. And this reveals a big difference between the Campo and the OSM networks. So even for links representing the same roads, the original Campo network has less freeway and expressway lane miles, and this is due to removing of auxiliary lanes and less controlled intersections than the version extracted from the OSM. But the original Campo network contains more lane miles for other arterial roads because they were inflated to adjust for missing links. Now we paired these 3 networks with 2 different types of addresses. So the OSM-based Campo network and the full OSM networks were tested with both Campo and open addresses locations, leading to 5 scenarios examined in the study. Now getting into the results, we'll look at the global network effects first between the Campo and the OSM networks. So this figure is called a network curve, and it shows the number of vehicles in the network for each second of the simulation. And first comparing the original Campo network, this is the version from the MPO, it's in red, to the version, to the same roads extracted from the OSM network in green. The original Campo network has 7% lower VHT compared to the OSM-based Campo network, but the same VMT. And the lower VHT is due to the inflated lane counts and fewer controlled intersections, which leads to less congestion, especially in the evening peak. Now comparing what happens when we add the full OSM network. This is depicted in blue. So overall, surprisingly, the VMT and VHT are relatively similar. But when looking at the links that are in common, which are the links contained in the original Campo network. Adding links reduces VMT and VHT on those roads by 11 and 16% respectively, which suggests that adding all the local roads leads to some decongestion due to the alternate paths that are now provided. Now getting into the shared autonomous vehicle operation results. On the bottom, we have a table showing some key performance metrics for SAV fleet performance in terms of the trips served per day, VMT for SAV, percentage of empty VMT, average trip distance, and wait times. And overall, the performance is actually pretty similar despite the differences in network congestions that we saw on the previous slides. One thing to know, however, is that on the original Campo network, trips are on average 1 mile shorter, which is quite big. When adding the full OSM network, the performance improves slightly. For example, VMT per SAV fell 5%, while the number of trips served rose 1%. Percentage of empty vehicle miles travel fell 2.3 percentage points, and wait times fell half a minute. Now comparing the effects of addresses, unlike what we saw when we compared the effects of missing links, there are no change in the VMT, VHT, or network loading when going from the aggregated to the real addresses. And similarly, the SAV fleet performance is very similar. So in conclusion, we observed major differences in lane counts and intersection control between the MPO and the OSM networks. And going from an incomplete network that is missing 60% of lane miles to a complete network significantly decongest existing links that are in common, but the network-wide VMT and VHT stay roughly the same. Relative to the differences in network congestion we saw among the networks, SAV fleet performance was surprisingly consistent, and using aggregated versus real addresses made no difference in terms of both the network congestion and SAV fleet performance. A fleet of 1,500 shared autonomous vehicles in the Austin 6-county region is able to complete around 28 trips with wait times of 5 to 6 minutes while driving 325 to 350 miles per day, of which 22 to 27% are empty. Yeah, thank you. Please let me know if you have any questions or comments.
Great. Any questions for Kentaro? Don't be shy. Okay, well, if any, yes, let me see. None. Donia, can you unmute? Let me see if I can do it. I should be able to do it. Where are you?
So I see a question about dynamic traffic assignment. Did the dynamic traffic assignment consider shortest travel time or shorter distance for the analysis? So the routing in Polaris is quite advanced. It's called the time-dependent A-star algorithm. I'm not 100% knowledgeable about it, but I can send you the paper if you're more interested in how the routing is done.
So I think you have another question from Mike Highland at UCLA.
Thank you, Taro. Interesting research.
Oh, thank you.
Do you have any thoughts as to why there is no difference in aggregating the addresses, the locations, compared to kind of dissipating them across the network?
Yeah, that's a good question. So are you referring to
Yeah, these results,
the
right?
SAB results or the network-wide results?
I think both, right? Because there's no difference really across any of the results.
Yeah.
Is it like a Polaris thing? Do you think?
Yeah. No, so I think if there were to be any difference, it would be due to how the demand from the addresses loads to the network. And I guess there wasn't much difference there in terms of like how those loadings contribute to the congestion.
Okay. And then for the like many more links in the network and a lot more addresses, how does that impact additional runtime?
Yeah, so addresses actually don't affect computational runtime at all, but adding those links, they do. So I think, let me try to pull up my notes.
If it's a factual answer, you could probably just tell me in the chat.
Yes. So between the OSM based networks, going from the clipped OSM network to the full OSM network, it was about 2 to 3 times the difference in computational runtime. But also there's a difference between the original Campo network versus the OSM based as well, because the OSM based OSM network has shorter links, so that also contributes to increased runtime.
Thank you very much.
Thank you.
Great. So I think, again, in the interest of time, if there's additional questions, we can have that discussion in the chat, and we'll move on to the next speaker, Priyanka Pithankar, who is also a PhD student at UT Austin with Dr. Kara Kokelman. So Priyanka, if you want to share your screen, and feel free to start whenever you're ready. Are you able to share your screen? Donia, you might have to make her a co-host. Oh, okay. I can't seem to make you a host. It might be, oh, I see. It looks like because I think Donia dropped out for some reason, Felix is listed as the host. I'm not sure why. But Felix, can you maybe see if you can make Priyanka the host then? I'm not sure why it would switch the host. Okay, well, let me see. Felix, sorry, are you still here? Don't know why it would have switched the host like this, and you should be able to have that control as a host. Priyanka, did you share your slides? Because maybe we could do that. Yeah, sure. Maybe just while we're doing that, let's switch the order. And Javier, do you maybe want to present next, and then we can have Priyanka present at the end?
Oh yes, I am.
Okay,
able to do it.
let's do that then.
I think now it's working, so I switched to be a host.
Well, we'll still have Javier present first.
Okay, so hello everybody. So my name is Javier Peña, and I'm going to present in behalf of my colleagues at the University of Alabama, and the presentation title is Enable Dynamic Ride Sharing in Shared Autonomous Vehicle Fleets, and a study of 200 small and medium-sized urban areas. So a little bit of background. When we were doing the literature review for this research, we found that most of the information that is available is centered on the larger scale cities with population of over 1 million. And then we found also that dynamic ride sharing is a less explored topic when studying shared autonomous vehicles. And this is an extension on the research that this session saw previously. So here the goals were different, and we have two of them. First is to complement the large scale city research, and the second one is inform local strategies and plans for deploying emerging mobility system. The expected outcomes are related to those goals, and mainly we want to know the factors contributing to the autonomous vehicles performances. And here is the conceptual framework. It starts with the organization and preparing data on regional travel demand and regional road network. With those two sources of information, we were able to model the fleet of autonomous vehicles and get some performance indicators in two scenarios. The first one is with dynamic ride sharing, and the second one is without dynamic ride sharing. Finally, we do statistical modeling to get some insights from this information. The data sources, as you imagine, and we saw previously, comes from information that is available to the public. The first one is the origin destination employment data published by the Census Bureau in the United States. The second source is the National Household Travel Survey to understand travel departure times. Sorry, what happened here? Can you see my screen still?
No, we're seeing your video.
Okay, it says host disable participant screen sharing. Okay, let me try again.
Yeah, try again now. I don't know what's happening, but it looks like Donia dropped out, so now you've been
Okay.
dismissed. Yeah, so just
Okay, so and finally, our last data source is the road network that we have obtained from a paper from Dr. Boyne in 2020. He extracted the shape and attributes from OpenStreetMaps for all the road networks in the United States. Here is an overview of the cities that are included in our simulation and the trips that were prepared for the simulations. And here a small example on why it is so difficult to generate a code that enables dynamic ride sharing on the simulation. So here we can see a car traveling with one passenger. It is expected to have a destination, but in the middle of the way, there is another traveler requesting a service, and the vehicle has to evaluate if it is possible to modify the route and continue with the two passengers. In this case, the car decides to go for the second passenger and continue their route. And then there is a third passenger, passenger C, also requesting a service. And the car also has to evaluate, again, if it is possible to modify the route. The criteria to decide that is a threshold time that was defined previously. So in this case, for example, the simulation does not go for the third passenger. The car A continues the previous route, and one new car is generated to pick up traveler C. So that logic is kind of represented in this diagram, and there are three important points in the flow diagram. The first one is in the top in yellow and green colors. The algorithm is going to evaluate if there are available cars in the time threshold. So it is going to be 5 minutes. If we know that there are cars available within 5 minutes from the location where people is requesting the service, we will have that vehicle as a possible option to pick up the passenger. And then in the second decision, we have to know if those vehicles that are available, once they modify the route, they will have a different in-vehicle travel time. So that change in vehicle travel time is going to be above critical travel time, which is also 5 minutes. And if that's the case, if one of those two conditions are not met, a new car is going to be generated by the simulator. But if the two conditions are met, then the car that is in the road is going to modify the route and continue to pick up an additional traveler. The final point in this flow diagram is the number of passengers that are allowed in a car. If there is still capacity, they will be in the group of available cars. If not, they are only cars on the roads. And with that framework, which extends the previous research, we also generated some fleet performance indicators. In the left, we have the metrics for one scenario. For example, we could evaluate the required fleet size, the number of trips per vehicle, and then we can see in the right-hand side of the screen some metrics for both scenarios, for two scenarios. In this case, for example, we can see the % reduction in required fleet size, the increase in average trips per vehicle, and so on. So all those outputs are generated by the simulation, and then we have to get some knowledge or some insights from that, and we use statistical models to get these final results. The statistical models use the road network characteristics, the travel demand characteristics, and also the outcomes from the simulation. As we know, we have many fleet performance indicators. So in this case, we are only going to do the regression or the statistical models for 4 of them: the average number of trips per vehicle, the percentage of MTBMT, and all of the 4 indicators that are in the bottom of the screen. And additional highlight point here is that the road networks could be included in the models as they are from the beginning, or we can do principal component analysis. In this case, we are going to use both of those presentations for the road networks and evaluate the models. So here are going to the results, the summary statistics, and we can see, for example, that in the scenario without DRS, the required fleet size on average is 3,400 vehicles. And then in the scenario with dynamic ride sharing, the required fleet size on average is 2,400 vehicles. So there is 1,000 difference in two scenarios on average. But also we can see that there is a 21% increase in personal travel time. So that's a drawback on this approach. And we explored these details further. In this table, I'm not going to cover more details, but we will see later some of those. For example, here we have two graphs. The left-hand side is the average trip duration compared to the average trips per vehicle, and we can see that with dynamic ride sharing, consistently there are a higher number of trips that can be served by one vehicle. And then on the right-hand side, we can see the average trip duration compared to the percentage of MTBMT. In this case, without dynamic ride sharing is negatively related, but in the scenario with dynamic ride sharing, there is no linear relation. And that's something interesting that we could find in this research. And here are the statistical models. In the left are the models for the graph measures as they are. And on the right-hand side are the graph measures with principal components after doing the principal component analysis. The other variables are identical between the two tables. And I'm going to just explain the left-hand side because it's clearer than the principal components. In this case, we are seeing the trips per vehicle model, and we can see that the proportion of dead ends is negatively related to that indicator. So in cities where the road network is complex and the cars need to travel or do detours, travel further, of course, the number of trips that they can serve will be fewer. And also, the trip patterns future are important. For example, the average trip duration is negatively related with the trips per vehicle. Longer trips mean fewer trips per vehicle. But one key point in our results is that cities with trip density, really high density of trips, are positively related to this indicator. So in those cities, the cars are more efficient. Here we can see a geographical distribution of those results for both the scenarios. The blue dots are without dynamic ride sharing, and the orange dots are with dynamic ride sharing. And there is no consistent pattern geographically, but we can see that in the west of the United States, many cities after the introduction of dynamic ride sharing increase the number of trips per vehicle substantially. So that's one of the key results also, because interested parties could target some cities according to these results. Shifting to another indicator, we have the percent of MTBMT, and we can see that the proportion of dead ends is going to increase the percent of MTBMT as expected. But also the trip density is going to reduce this indicator. So again, those are findings that are important and need to be balanced by, for example, companies trying to enter the market with this type of services. And here are the changes between the two scenarios. Again, cities in the West and in the middle in the United States are cities that display substantial change after the introduction of dynamic ride sharing. I'm not going to talk about this indicator, but it has the same logic. But here is the the geographic distribution for the increase in trips per vehicle. So again, some practitioners or policymakers could leverage this information to get or to make some policies in the future or currently actually. And the final indicator is the percent increase in personal travel time. So in this case, we are measuring what would be the effect on the person that is traveling. And it is really important because many people will choose not to use this type of services if they are facing long detours or long extra time. So again, key variables on the models are proportion of dead ends, the three-way intersections in the city, and also the trip density. If trip density is high, there will be a lower increase in personal travel time. So those cities that have this component could be targeted for pilot studies or introduction of these services on early stages of these business models. So with that, also we have a geographic display of those results. And finally, we land to the conclusions. In this case, the dynamic ride sharing implementation improves the efficiency and reduce the operational cost of autonomous vehicle fleets. However, the personal travel time is negatively impacted by this type of policies. So these policies should not be included in all cities. But this type of research allows to do some discussions and evaluate the possibilities and challenges of these services. It is important to highlight that high-density trip areas are ideal for dynamic ride sharing. And I think that's my presentation. Thank you for listening, and I will be happy to answer questions from the public.
Thank you, Javier. I think it looks like you were switched to being the host.
Okay.
Can you make Priyanka a co-host?
Yes, I will try to.
Okay. I think Donia is having some internet issues, so.
Co-host.
Yeah.
So here we are. She will be able to share her screen.
Perfect.
Thank you, Javier.
And then I know Priyanka has to leave because she's chairing a session in 15 minutes. So we'll give her a little bit of time to present, and then if there's questions for Javier, we can answer those in the chat or at the end after Priyanka has to leave. Okay, go ahead, Priyanka.
So thank you, Jason. Hello, everyone. I'm Priyanka. I'm fourth year PhD student, advised by Dr. Kara Kokelman, and our co-author, Maitri Velimena, who now works at Atkins as data scientist. So this work is in collaboration with TextDot. My previous presenters have given a detailed overview on what AVs and SAVs are about. I will go further and talk about impacts of these vehicles on Texas, on long distance travels, and also the mode and destination choices. So, oops. So as we all know, AVs are going to make driving easier, and hence is going to increase the vehicle's miles travels all over the world. They may also reduce crashes per VMT by 80%. They can increase the access to elderly and impaired people, and perhaps can lower the emissions too. Autonomous trucks can increase the operating hours, both by distance and number of working hours, making them a competitive mode in the market. So this study integrates AVs, SAVs, and autonomous trucks in TextDot's statewide travel demand model and analyzes its impact on the transportation network. So we will be comparing the AV scenario with no AV scenario, taking 2040 year as a target year. So SAM is basically a multimodal travel model. It's developed by Aliens and it's maintained by TextDot. Its version is operating on Transcat 8.0 and it's a weekday module and we will be comparing scenarios for 2040. It covers North America, focusing mainly in and around Texas, which has over 200,000 links and over 6,000 TAZs. So it has two parts. One is passenger model and another is freight model. So both of these parts follow a four-step travel demand model. So it goes from trip generation, distribution, mode choice, and assignment. After mode choice, the freight trips and passenger trips are combinedly loaded onto the Texas network. And SAM uses four time duration windows. So morning is between 6 to 8 a.m. Afternoon is 8 a.m. to 2 p.m. Evening is 2 to 6 p.m. And the midnight will be 6 p.m. to 6 a.m. So we are in this study, we are assuming short trips to be within 50 miles one way and long distance are over 50 miles. It can happen over several days. And this model does not capture the non-freight truck trips, which are less than 50 miles. And we are expecting it to be local delivery trips. So the freight model, it's based on 2015 Transurge data. So it has 5 modes: truck, car, load rail, intermodal rail, water, and air. It uses incremental logit model and has 15 commodities that includes all those 5 modes. So commodities includes agriculture, paper, chemicals, petroleum, etc. So the freight model, it's basically approximately 350 by 350 matrix, which contains 254 Texas counties, 49 US states. We have DC, 32 Mexican states, and 13 Canadian provinces. Whereas passenger model, it's much bigger, has over 6,000 TAZs. So we will have approximately 7,000 by 7,000 matrix for the traffic assignment here. So our base scenario is one with the default text.sam settings, which will serve as a benchmark to compare the AV scenario, which will have drive alone and also shared AVs, SAVs, and autonomous trucks. And we will be analyzing results for the typical weekday of the 2040 region, 2040 year. So for the short trips, SAM has a fixed mode splits, and those are going to remain same even after the AV introduction. But for the long distance trips, it has a nested logit model, and we have added human-driven autonomous vehicles along with human-driven in drive alone and shared rides branch. So the parameters of this nested logit model is based on Yantahu Hong's Texas mega region study back in 2020. For freight mode choice, we have integrated a truck in a truck branch with nesting coefficient of 0.7 to show a relative substitution between these two. We are assuming its cost to be 50% higher than human-driven truck, but they also have 25% reduction in value of travel time. To show continuous operation of a truck, because they don't need any, because now with the removal of driver, there is no need to the rest time. We are keeping travel skims at 42% of what human-driven truck would take. So for our analysis, SAM is assuming that in 2040, Texas will have 40 million persons residing in 13 million households, working 19 million jobs. And we are also assuming the trip production to be increased by 15%. And this assumption is also based on Yantahu Hong's Texas mega region study. We are also assuming 60 miles per mile as an operating cost for personal AVs, $1 per mile for SAVs, and A trucks will be 50% more expensive than H trucks with reduction of 25% in VOTT. So going on to the results, if you look at the percentage mode shares between ground travel versus air versus transit, we can see that there is overall increase of 30% in ground travel, but we can see significant increase in share rides, which has more than 3 occupants, specifically for business and non-business trips within 50 to 500 miles. The person trips have increased by 44 and 34%. We can also see a reduction in air trips between 50 to 400 miles trip bracket, 35% for the business trips and 30% for other business trips. So we can see the mode shift happening from air to ground. If you look at just the ground travel, we can see 17 percentage point decrease in human-driven vehicle person trips driving alone, and AVs on an average enjoying the share of 14% after their introduction. We are also expecting the increase in average trip distance for business trips to be 18% if the trip is between 50 to 500 miles, while for non-business trips, this rise is 13%. For the trips more than 400 miles, we don't see much increase, as there won't be much mode shifts there. And yeah, so these vehicles are also going to increase vehicle miles traveled by 26% on an average, with morning and evening vehicle miles going to increase by more than 25%. We also see increase in trip length in terms of freight trips. So the trips with light duty trucks, the travel distance per trip is increased by 35%. For medium duty trucks is 32%, and for heavy duty it's 28%. AVs are also going to add passenger miles traveled. We can see that if you're driving alone, AVs have carried almost 35 million person miles. And similarly, if you're sharing a ride with another passenger, AVs are going to AVs made up for almost 7 million person miles. At the same time, they're also going to cause decrease in average speeds on all types of roads, specifically on interstate freeways, where we can see 58% reduction in average speed in the morning hour and 60% in the evening hour. We are expecting a very high congestion with significant increase in vehicle hours traveled during morning and evening times, because they are increasing by more than 250% in both cases. In case of freight mode, air trucks are clearly winning. They are carrying 77% of tons in case of non-durable manufacturing commodities, followed by 65% in case of food commodities and 69% in case of consumer manufacturing. If you look at ton miles moved versus between A trucks versus H truck, so we can see 65% of reduction happening in case of commodities carried by human-driven trucks, whereas autonomous trucks are carrying over 1,000 ton miles commodities. And we can also see some reduction in other modes. So to conclude the study, we are expecting that people are going to choose more remote locations. We can see 18% rise on an average trip length for business travel. It goes from 121 miles to 142 miles on an average, whereas for non-business trips, that increases 13%. AVs and SAVs together, they account for 14% of one-person trips across Texas, and HV trips are going to experience fall of 17 percentage point fall in their mode shares. SAVs with more than 3 people, they make up 14% of 300 million person miles traveled between 50 to 400 miles, while 2-person SAVs are make up for almost 8%, and 1-person AVs have share of almost 11%. A trucks is completely popular in a freight mode, handling 35% of Texas ton miles, followed by 16% by human-driven trucks and 24% by rail. We are expecting a serious network congestion if the demand management measures such as congestion pricing is not in place, with daily VMT rising by 24% from 1.1 to 1.4 billion vehicle miles per day, and with average speeds falling by 37% on an average if they are weighted by their VMTs. So thank you, and I will be happy to take any questions if anyone has.
Thanks, Priyanka. I know you have to run to another session, so I'll post a message with Priyanka's email. So if you have questions, you can maybe reach out to her by email.
Mhm.
Do we have